Hello everybody, Andy Fowler here from Sigma-HSE. Hope you're all keeping well and busy, and thank you for joining us for one of this month's webinars where I'll be discussing how we go about identifying appropriate fire and explosion hazard data for your unit operations. For those of you who have joined us previously on other webinars, undoubtedly you'll have sat through myself or my team discussing the different types of tests to get a grip on fire and explosion characteristics, particularly with regard to substances. I won't be going through that in any great detail today, but building upon that knowledge, hopefully, that you've already got. So just to introduce myself formally, I'm currently the Technical Operations Director in the Winchester headquarters in the UK for Sigma-HSE, and you can see my short biog there. I'm getting a bit old in years now. I'm getting close to over 40 years experience in major hazards and process safety, and this is just one aspect that I'll be dealing with on the DSEAR or fire and explosion characteristics today. But as a company, we do work anywhere in the world, and we've got various offices and laboratories around the world. So as I said before, headquartered in Winchester in the UK, but we've got offices in India and in the northeast of the US where we can provide our services. And we've also got laboratories, so we do run accredited laboratories for undertaking the appropriate tests for fire and explosion and electrostatic hazards and things like that. And we do that either in our laboratories in Winchester or over in India. So we consider ourselves experts in this topic, providing consultancy on all aspects of process safety, whether that's developing process safety management systems or helping you build an appropriate management of change system, these sorts of things, as well as doing ATEX or DSEAR or DH assessments in the States associated with specific legislation. And as I say, we've got the laboratories, and of course, because of our experience, and there's not many processes that we don't come across, we do actually do a lot of bespoke training in all of these aspects. But we are very lucky, and different to most process safety consultancies is that we have the laboratories with trained technicians, accredited systems, and the proper kit and looked after well to be able to do the tests all associated with the correct and appropriate standards. So nothing's made up, although we can do bespoke testing, but in many respects the data that I'll be talking about today, the test protocols required are all laid down within appropriate either BSI, ISO or ASTM standards. And you can see that we span not just powder and gas and vapor fire and explosion properties, but also electrostatic properties, thermal stability testing, and chemical reaction hazard testing. So we've got our own Carious tubes and DSCs and various types of calorimeter to really get a good understanding of chemical reaction hazard. And of course, we couple that with our consultancy services, where we go out and help clients on their processing operations. And as I said before, that can be anything from carrying out assessments such as hazard, HAZOP, LOPA, functional safety, or any aspect of process safety management, implementation or review, and so on. But today, I'll be covering specifically fire and explosion hazard data necessary dependent upon the different types of unit operation, and I'll cover that off at the end of the system. But we will have a look at, well, just what is a fire and an explosion fundamentally, and then how then We can use the data that we can determine during the tests, and in many, it's fair to say that in the data that's appropriate really can't be calculated. It's something that needs to be tested and use the experimental results, which is why being an accredited laboratory is important, because we can prove that all our sensors and equipment is calibrated correctly and so on and so forth. So that's what I'll be covering today. So we'll start off with looking at, just what is a fire or explosion. And many of you will have heard of the fire triangle. Very simple little approach. But really, from a chemist point of view, I look at it slightly differently, perhaps. But I'll give you a flavour of that as we go on. So within the fire triangle, we require a fuel. We require something that can burst into flame or explode. So this is the substance. Okay, so it could be any material that's classified as flammable under things like the CLP legislation or similar legislation around the world. And that flammable material could be a dust, powder, it could be a gas, it could be the vapours from a liquid. It's important to realise that liquids really don't burst into flame. It's the vapours given off from the liquids that burst into flame. Because it's all right having a fuel, but we need the second part of the triangle. We need an oxidant. We need to be able to react that fuel, generally with air, but any oxidant really. So there's a variety of ones. And to kick all that off, we need an ignition source. So we can mix the fuel vapours with air, but we've got to put energy into the system, which is known as our ignition source. Now, from a chemist point of view, the fire triangle, this is combustion. Something bursting into flame or explosion is simply just a chemical reaction. It's the reaction of a material that's capable of reacting with oxygen. It's an oxidation reaction. Okay, so obviously, if a fuel is already fully oxidized, like calcium carbonate or a sulfate, something like this, it's already fully oxidized. It's not capable of reacting further with oxygen or air. And therefore, that sort of material, chalk or something of that ilk, won't be a fuel, cement, dust or whatever. But there's many, many other materials, especially in solid form, where they can react. Many common materials can react with oxygen, burst into flames. Things like sugar and flour and paper dust and cellulose and all of this sort of stuff. So it's just a chemical reaction, and with all chemical reactions, what we need to make that reaction efficient is we need good mixing, which is where really we're looking at a gas-gas or vapor-vapor reaction. And we need to impart sufficient energy. We all know, for instance, that when we're doing chemistry in the laboratory or whatever, generally we need to heat the liquid materials up to get them to react. We need to put in some energy. From a chemist point of view, it's the activation energy. Okay, but any ignition source can give that sufficient energy to ignite that fuel oxygen to kick off that combustion reaction, the reaction of the fuel vapours with the oxygen. We need to impart energy. And because the oxidation reaction is an exothermic process, it gives out heat, and this is where we get our flames and we get the fire and the explosions that we all know and love. And when we look at the standards associated with this subject, they list 13 potential sources of ignition. But what determines whether a given ignition source will actually kick off this reaction is how much energy it can give versus how much energy is actually needed to start the chemical reaction. So if you look at it from a graphical point of view, we start off with the reactants, the fuel and oxidant, at a certain energy level. If they were to react, they will end up at a lower energy level, having kicked out a lot of energy in the form of heat and flames. But generally there's a hump we have to get over. As a chemist, I know it as the activation energy. But in this sort of, when we talk about it in this context, we generally talk about the minimum ignition energy. Can those different sources of ignition, potential ignition sources, can they provide sufficient energy? Because not all ignition sources are the same. Some will give quite a lot of energy out, others will give out very little energy. And similarly, that fuel-air mixture may require a lot of energy to kick the reaction off, or it may indeed only require very, very small amounts of energy before we can kick that reaction off. But if the reaction occurs, we can end up with a fire. Now, the other side of it is we can not only can we have fires, but we can have explosions, which starts off with the fire triangle, but adds in a couple of extra things. We end up with what's called the explosion pentagon. We talk about we've got to have good mixing. We've got to have that fuel and air intimately mixed. Easy when we're talking about vapors and gases, because they'll mix readily together. When we're looking at powders and solid materials bursting into flame, then really we need to be able to disperse those solids so they form a cloud, like a dust cloud. And that gives us that mixing. And the other way that we need to develop an explosion, and the only difference being, obviously, you still get flames in an explosion, in this type of explosion anyway. But we also get explosion overpressure, and that comes about either through confinement or indeed congestion. So what do I mean by that? If I have a fuel-air mixture out in the open air and I have an ignition source and kick off that combustion reaction, you'll be able to watch the reaction occurring. You'll see the flames burning relatively slowly through that cloud of fuel-air mixture. That's known as a flash fire. Okay, but there's nothing there to stop the expansion. I mean, obviously that mixture, that fuel-air mixture will expand as it's on fire. The fireball will grow. It grows either because it's getting hot, and we all know that things expand when they get hotter. It can also expand because we may generate more moles of combustion gases than we started off with. Okay, but there's nothing to stop that expansion if we're out in the free air. If, however, we're confined, that explosion occurs within a piece of equipment or in a room or a building, then what happens then is we can get flame acceleration. And it's flame acceleration that leads to explosion overpressure. It's the changes of surface area of the flame because it comes across obstacles it can't get through. Okay, that causes more turbulence, more mixing. We increase the surface area. If standard physics, if we increase the surface area, we get changes in velocity. Velocity is a vector, so effectively we're accelerating the flame. And it's then very much down, put in a different context, it's basically Newton's second law of motion. If we accelerate a mass of flame, we will end up with a force, and the force is the explosion overpressure. Now, I've got confinement on the slide. It can equally be done by what's called congestion. And all that really means is the flame isn't confined, but as the flame travels through space, it comes across obstacles which it can't get through, so it needs to accelerate around. So as flame goes, if you had a fire explosion starting off in your processing plant, it will come across vessels, tanks, pipes, building stanchions and so on, all of which will accelerate the flame as the flame accelerates around those obstacles, and that will result in explosion overpressure. So we generate that explosion pressure and we can start blowing things apart, blowing the walls out of our buildings or so on and so forth. So that's just some fundamentals of our explosion pentagon. And clearly, if we can remove any one of the sides of the fire triangle, the combustion reaction can't occur. And if we can stop mixing or stop confinement or congestion, we'll only end up with a fire and not an explosion. Okay? And that's really what a lot of the regulations out there in the world are trying to make it safe, that you as a human aren't impacted by the impacts of fire and explosion, primarily by trying to prevent the combustion reaction in the first place. But if it does happen, because we live in a risk land, we can do our best to prevent fires and explosions, but they may still occur. Then we can use techniques to make sure that you're not hurt by those hazard impacts, by having vents, for example, on our vessels or things like this. So when we look now a bit closer at the sort of data that we need, we really need to know for the materials that we're playing with, whether they're liquids or the vapors from liquids or gases or powders, we need to understand, are they our concern or not? Can they, first of all, undergo this combustion reaction? If they can't, because we're dealing with something like cement or water, not capable of being oxidized readily, then, there's not a problem. We don't need to fuss about fire explosions. If in fact they can, then we only need to understand more, because we've got to try and prevent that happening and try and stopping the fire. And we can do that by either trying to prevent the flammable atmosphere, that fuel-air mixture, because we could do that, for example, by inerting the system, removal of the oxygen, or working at low temperatures or this sort of thing, or working under vacuum. If we can't do that, if we can't avoid our flammable atmosphere, then we specify equipment which has got a much lower probability of that equipment acting as a potential ignition source. And this is where you'll have heard about ATEX certified equipment, ATEX switches, ATEX valves. These are all built to a specification that reduces their probability of ignition. Doesn't eliminate it, but it tries to reduce the probability of it. Okay, and we need data to be able to do that. We need data to be able to design our vents correctly or our containment systems correctly. Now, when we're looking at flammable liquids, and many of you will have storages of flammable liquid in one way, shape or form, one of the major first pieces of data we need to know is the flash point, the lowest temperature that material gives off sufficient vapors, which if they mix with the air will ignite if we give it an ignition source, okay, known as the flash point. And in the legislation in the UK and Europe, we classify something as flammable if it's got a flash point of less than 60 degrees C. So that means we need to heat that liquid. If that liquid gives off sufficient vapors at temperatures less than 60 degrees C to mix with the air and be ignited, then it's a flammable material. If we need to heat that liquid to temperatures greater than 60 degrees, we won't classify it as flammable. Of course, in your process, you may be deliberately heating that liquid above that temperature, and therefore you'll have a flammable atmosphere if air is present. Now, a lot of this, when we're dealing with liquids and gases, in a sense, that work's been done for us because of the things like the classification, labelling and packaging regulations, where materials will have been put through a raft of tests to determine, for example, their flash point. And once we know the flash point, if it's below 60 degrees, we'll classify it as a flammable liquid, and you'll get a sticker on the container, and it'll tell you this in the MSDS data, telling you that it's capable of bursting into flame. Okay, but clearly, if we do know the flash point, and if we can make sure that we handle that liquid at temperatures below the flash point, there's not a problem. Okay, it's as simple as that. And we tend to designate under the various regulations out there, not just flammable, but between flammable, highly flammable, and extremely flammable liquids. Yeah, so essentially as we go down the rows in that table there, the materials are becoming more volatile, give off more vapours, hence mixing with the air at lower temperatures and become a lot more capable of bursting into flame. The other piece of data that's important for liquids is the auto-ignition temperature. So again, done in specified apparatus under specified test conditions, but it's the lowest temperature that vapours of a material will ignite without an ignition source. So this is basically saying, the auto-ignition temperature is saying, if your only source of ignition is heat, not a spark, not a flame, but if it's just heat, temperature, then if you've got a temperature greater than the auto-ignition temperature, the material is likely to burst into flame. Okay. It's important to realise also, I should have mentioned when I was talking about the flash point, the flash point is the temperature, is quoted in degrees C, it's a temperature reading, but it's equivalent to the lower explosive limit, which is the concentration of vapours in air, the percentage concentration vapours in air, the lower explosive limit or lower flammable limit, you'll sometimes see it stated as. Okay, so quite simply, just with those two pieces of data, if we're operating at temperatures above the flash point or concentration of fuel vapours above the LEL, and there's air present, we've got what's known as a flammable atmosphere. We've got that mixture of fuel and oxygen, where if we had an ignition source of sufficient energy, we could end up with a fire or explosion. Okay. When we're dealing with dust, pretty similar. The first thing we need to know is whether or not we have a combustible dust, whether or not that dust will react with oxygen. And in a sense, a good chemist should be able to look at the substance, and look at the formula of the substance and work out whether or not it's capable of being oxidized with oxygen. But generally it's done in a simple test, what's known as the Group AB test, where we deliberately take the finest dust of the powder, we disperse it in air to get that mixing, and then we stick a very large electrical ignition source through it. And if it bursts into flame, as the picture shows, then it's a Group A dust, it's a flammable dust or a combustible dust. If it doesn't ignite, it's a Group B dust. In a sense, that material's inherently safe, we don't need to bother about anything. But really, to create that dust cloud, just like with vapours, we need to be above the lower explosive limit and between the lower explosive limit and the upper explosive limit. It's exactly the same with dust. We know it as the minimum explosible concentration. So we've got to have sufficient dust in the air, and to be able to get that powder into a dust cloud so it's dispersed in air, we're really talking about the dust. We're talking of particle sizes less than 500 micron. If you're dealing with granules and things like this, very little dust present, again, the combustion reaction shouldn't occur because we can't get sufficient fuel into the system to make it explosible. So the temperatures, we can put energy in when we're doing a group A/B test. We're putting energy in the form of a spark, and that's often the case, but it doesn't have to be. It could be a temperatures as well, just like the auto ignition temperature, and I'll get to that in a minute. The other thing we know we need is an oxidant, generally air, but doesn't have to be. And of course, if we work at vacuum or we remove all of the oxygen, then we can reduce the possibility of it bursting into flame to zero. But in practice, there's what's known as a limited oxygen concentration, which of course is different for different materials. So standard air, for example, is 21% oxygen. Some materials, if you operate below 15% oxygen, then it won't burst into flame. Other materials, you have to go down to below 5% oxygen. Okay. And similarly, because again, it's a vapor gas explosion, in a sense, then if we increase the oxygen, we all know that we can increase the explosion severity that occurs. When we come to ignition sources, I said the standards point us to 13 ignition sources, all of them coming up here. So essentially, it's anything that can cause temperatures, any flames, any sparks, whether they're generated by mechanical friction or thermite, anything that can generate temperatures, whether that's hot surfaces or adiabatic component, or sparks of one way, shape or another, and basically any form of electromagnetic radiation could act as an ignition source. So there's lots of ignition sources, and as a process safety professional, you know, we're brought up believing that in terms of the hierarchy of control, trying to prevent ignition sources is relatively low on our agenda. We need to focus on removing the fuel air atmosphere if we can. And the reason for that is, as this slide illustrates, there's lots of potential ignition sources, and it is very difficult to eliminate all of those potential ignition sources all of the time. But we can do our best. And our best is using potential ignition sources where the probability of them acting as an ignition source has been reduced. And that's essentially what ATEX equipment does. The next stage of the pentagram was looking at mixing. Okay, so often we get good mixing deliberately within our processes, within our equipment, within our mixing vessels. We get that ventilator, or we ventilate systems, or we have extraction systems and things. The important thing here is particle size. Yeah. If you picture an iron bar, we can heat it up to extremely high temperatures. It doesn't burst into flame. It'll glow red hot or white hot, but it won't burst into flame. If we start grinding that iron down and we produce iron filings, if you remember back at school when we all used to tip iron filings into a Bunsen burner flame, and that basically the whole fireworks industry relies on such effects, we could get burning phenomena. And if I grind iron down to a very fine powder, effectively it becomes pyrophoric. It will burst into flames as soon as you take the lid off the container. And that's because particle size affects the surface area. That means the oxygen can get to the fuel source very easily over a wide area. and therefore that combustion reaction can be kicked off just because of particle size effects. Okay, so you'll note that whenever we do tests on the explosibility of powders, the test methods require us to sieve the material down to less than the 500 micron. In fact, it's down to about 63 micron that we tend to do the testing on. It's the worst case. And it's important to note that we can't calculate the effect of particle size. We've got to test it. There's no alternative to it. So given those attributes, that just illustrates what I mean by the surface area increases per volume. So any heat that's generated by the oxygen reacting there cannot be lost, cannot be conducted away into the bulk of a powder. So the heat will be generated almost adiabatically, and hence the exothermic reaction will go to completion very rapidly. The larger the granule, the less reaction occurs, less heat generated, but also the heat that's generated will be conducted within the body of the volume of the particle, and that will stop it from bursting into flame or exploding. And confinement, well, of course, you know, most of our processing equipment is confined, especially when we're dealing with potentially dangerous substances. We don't work in the open, okay? But if we can limit that concentration, if we can work with dust, if we work with dust greater than the minimum explosible concentration, or with gases and vapors above the LEL, we'll be generating that flammable atmosphere. So on the converse side, if we can ensure that our powders are well below the minimum explosive concentration, or our temperatures or vapor concentrations due to extraction and ventilation that we install into our equipment, we can ensure that we keep below these concentration limits. And then we're safe. Simple as that, really. But as I said right at the opening, if we have flammable dust, if we want to have a flammable atmosphere containing dust, we need that concentration above the explosive concentration, and we need the particle size to be less than 500 micron, because if particle sizes are larger than 500 micron, it's a lot more difficult to get that powder particles dispersed in air and producing that dust cloud. But there are many, many common powders that are flammable. They're capable of undergoing that organic reaction with air. Okay, it's as simple as that. So the testing that we do for powders, it's a bit more difficult, because the difficulty is dusts are not homogeneous. We can create those dust clouds, but they're not homogeneous, so we have limits to it, so we need to do the accredited techniques. You will find if you go into the literature, you'll be given various data for various types of powder. The difficulty is that literature very rarely gives you any further information as to the particle size distribution or anything else. Okay, so it's hard to work off the technical literature. For example, there's very many different types of flour, all of which will have totally different minimum explosible concentrations, minimum ignition temperatures, and so on. Primarily because of particle size distribution, but also other factors as well. We can only get at this by testing. So the testing that we do on a typical powder would be looking at what's known as the layer ignition temperature. This is just a powder, a layer of powder, a 5mm layer of powder that we sit on a hot plate, and we note the temperature at which the material starts to burst into flame. Okay, so this will mimic, if you're not very good, the energy source is a temperature, So, you know, if you have layers of powder sitting on top of your electrical motors or things like this, or steam pipes, then this information can be used to tell you whether you can have a fire event. We can also measure the minimum ignition temperature, which is the temperature required to produce ignition of a flammable dust cloud. It's a cloud phenomena. It's the energy source is purely the temperature that gives sufficient energy to kick off that combustion reaction between the solid fuel and the oxygen. And then we have the minimum ignition energy, the MIE, which is a spark ignition. And typically when we're measuring MIE values, we can do it in two ways. We can generate that spark that we put across within the dust cloud. We can generate that spark either capacitively or via an induction method. And the reason why they're done differently is because they mimic different types of spark, essentially. When the spark discharge is done capacitively, it mimics electrostatic sparks. When it's done via an induction mechanism, it mimics frictional sparks, impact sparks, and that sort of thing. Yeah. The only difference really between the two is the time at which the spark is discharged through the dust cloud. Okay. So minimum ignition energy is very important, because once we know the minimum ignition energy, we can then consider our ignition sources, and if those potential ignition sources can't give sufficient energy in relation to the minimum ignition energy, then they can't become an effective ignition source. If it requires 1,000 millijoules to ignite that dust air mixture, the MIE of the powder, for example, or the vapor or the gas, if the energy source, say a person who could only generate 30 millijoules, it's a lot less than 1,000 millijoules. That means that a spark discharge from a person has got insufficient energy to kick off that combustion reaction. If we're going to prevent confinement and congestion and deal with it, either through what's typically known as the basis of safety, which can be containment. We contain the effects of the explosion, it doesn't leave the containment system, or by venting, or by suppression, then we need data such as the maximum pressure that explosion could develop, what's known as the KST or ST class, and this is basically the rate of pressure development over time. The steeper that is, the more violent the explosion is. And we need to use this sort of data for determining the size of our vents and how quickly our vents need to open, and so on and so forth. If we understand the minimum explosive concentration, we can perhaps design our systems to operate where we keep the concentrations below the MEC, the minimum explosive concentration, or indeed the LEL if we're looking at vapors or gases. If we know the limiting oxygen concentration, we can start inerting our systems or working under vacuum to prevent ignition, and so on and so forth. So there's various changes. Now, when we're dealing with liquids and gases, it's easy to go to the technical literature. You don't necessarily need to test for flash point or to ignition temperature, for example. Most MSDSs that you'll get from the suppliers of your liquids and other materials are likely to have flash point and auto ignition temperature. If they don't, you can search in the literature. Okay, this isn't necessarily the case when we're dealing with combustible solids. Your MSDS contains simple words saying be care, the dust may ignite at high temperature or whatever. And this has been picked up by the EU, and recently they have asked that safety data sheets include more of this data, especially when we're dealing with combustible dust. That the MSDS should contain things like minimum ignition energies, layer ignition temperatures, minimum ignition temperatures, Pmax, and so on, and the MECs. Okay, I can tell you now that even though this change to the legislation has been around since January 2021 and active, most MSDSs that I see for combustible solids does not contain this data. At least now it means that rather than doing expensive testing, you should be able to go back to your supplier and say, do you know about Annex 2 of REACH? Because you're supposed to provide this sort of data and get them to foot the cost for doing this testing and giving you it for their particular materials that they supply to you. If you can't get that, I'm afraid you've got to do it yourself. You've got to get the testing done. And as I say, some of this testing is important because especially if we're going to move on to the basis of safety, trying to protect ourselves from the impacts of fires and explosions by venting systems or suppression systems or containment systems, then for them to be effective, they need to be designed properly. And you can only design it properly if you've got sufficient data and the correct data. Some things are relatively simple if you can change your processes. If we can replace the fuel with a non-flammable, or one liquid of one flash point with a liquid with a much higher flash point to do our processing operations, inherently we can be safer. If we can get the oxygen atmosphere down by the use of vacuum or inertion with nitrogen, for example, we can make ourselves safe. If we can provide ventilation that will deal with the concentrations we expect and keep them well below the explosible concentrations, that's fine. If we can prevent the powders being dispersed into a dust cloud because we use them damp or in paste form, or we use larger particle size materials, then that's all good means at which we can prevent that explosion. As well as using, if we can't prevent that flammable atmosphere, then the legislation points us to using ATEX certified equipment that's specifically designed to reduce the probability of that equipment becoming an ignition source. Okay, and that is done in two ways. We can do it when we look at it from the energy input being temperature, we can look at hot surfaces and we can build equipment that will only generate sufficient heat. So you can get electrical motors, some of which will run very hot and others will run at a much lower temperature. This is known as the temperature class. Okay, for vapors and gases, we tend to talk about temperature classes T1 to T6. T1, for example, says that heat could be generated at the equipment that's, I think it's about 415 degrees C, whereas T6, the equipment won't get hotter than 85 degrees C. Okay, now we use that information with our knowledge of the minimum ignition temperature and the layer ignition temperature, and we do this simple sum to put some safety factors in to get that. So we can prevent hot surfaces by having equipment of an appropriate temperature class or maximum temperature that it can achieve. If we're looking at ignition sources, electrical ignition sources, then of course we can we can ensure that we use ATEX certified equipment specifically built to reduce the probability of ignition. And ATEX certified equipment is needed. It must be installed and maintained and inspected by specifically competent personnel to keep it effective. We've got to make sure that we look at it occasionally and take appropriate action to keep it effective. Explosion protection is dealing with the ignited event, and those are the three typical means of doing that: containment, venting, and suppression. This is why if we're going to use containment, we need to understand the maximum pressure that that explosion can attain. If we want venting to be effective, we've got to make sure the vent is of sufficient area, opens at a low enough pressure so it can deal with the rate of pressure rise that's occurring due to the explosion in the equipment. And suppression, we need to detect the ignited event very quickly and put it out by injecting in extinguishant. But all of these three methods needs to have equipment installed to stop that explosion propagation going up or downstream through to connected plant and making things worse. So we need some sort of explosion isolation. So containment, building pressure vessels basically have their good points, but of course also have some very bad points, can be very expensive. There'll be pressure equipment, so you'll have to deal with specific legislation and so on and so forth. More used on vapors and gases than they are on powders, but can be. Venting, very typical that we can use venting to keep us safe, so the impacts of the fire and explosion leave the vessel, so we're not generating missiles from the processing equipment. But of course, the flame and pressure that comes out the vent needs to be to a safe location. And suppression, put it out as quickly as we can find it. Okay, so that's the standard of approach. But of course, dependent upon the unit operations that you're considering, you don't necessarily need all of that raft of testing data that's necessary. Okay, so if we look at some just finish off by looking at some typical unit operations. If we look at extraction and dust collector, yeah, and remember, extraction and dust collection is collecting the finest particle sizes. That's the reason why you've got the extraction and dust collection there. So it's the most combustible material. So your minimum explosible concentration in your ductwork between your process and your dust collector needs to be below the minimum explosible concentration, which is easy to achieve. You just need to know how much dust you're going to produce against the airflow that's provided by your ventilation. The minimum ignition energy is important because obviously if it's metal equipment, it could become charged if it's not correctly earthed, and the lower the minimum ignition energy, the easier it is that it's ignitable, that your powder's ignitable. But the solution to this is understanding just what the minimum ignition energy is, and then essentially making sure that everything that can be earthed is earthed to take away that charge. Okay, and of course, because in a dust collector, when you clear the filters of dust, you will be creating a flammable dust cloud, which if that ignites will result in an explosion because it's a contained system. You will have some means of mitigating the effects of that, typically a vent, and that's where you'll need KST and Pmax data to be able to design that vent or suppression system or containment system appropriately. If we were just dealing with the simple thing of manual handling of powders, you know, where we're scooping materials from a sack into a weigh hopper, or we're weighing material out and things, then again, if we have controls on the minimum explosible concentration and understand the minimum ignition energy, this will point us to the necessary controls we need against earthing to prevent ignition, and necessary controls we need to prevent explosible atmospheres within the concentration limits being developed. Okay, we don't need to bother about KST and Pmax and things like this for that typical operation. Similarly, blenders, mixing, again, MIE is important, and because the material, the resistivity of your powder or the resistivity of the liquid and how quickly that can decay its charge, that will have an impact on the likelihood of having electrostatic ignition sources. So MIE is necessary there to understand. That sets the limits on our system. Explosion severity is important, so we'll need to understand the KST, the Pmax. Within a mixer or blending operation, we will be creating dust clouds. So the minimum ignition temperature is important to know. So we can relate this, for example, to the bearings or the agitator mechanisms and so on, making sure that they don't run too hot, don't reach temperatures that are in excess of the minimum ignition temperature. Or we could also perhaps put some inerting in or operate under vacuum, or where liquids are concerned, cool the blender or mixing operation down to prevent those vapors or dust producing a flammable atmosphere. For powder milling, of course, there we've got high moving hammers or knives within the mill that can generate heat. So MIT is important. Could have layers sitting. There'll be a lot of heat input, a lot of energy input to a milling operation, so the powders can get hot. They could ignite and have KST and Pmax, so we can either make the mill capable of handling those pressures, containment, or we can vent them. Ignition sources from electrostatic means can occur, so we need to know our MIE. And again, we could, if we wanted, work under inert atmospheres. And then moving on to liquids, the important thing here is flash point and auto ignition temperature. So, you know, if we were storing a low flash point solvent, very typical in our processing industries, acetone, toluene, xylene, alcohols, all have flash points round about 12 degrees, which in the UK means that for a good part of the year they're giving off sufficient vapors. There'll be the flammable atmosphere will be present, so we need to control our ignition sources. We may have bearings or sources of heat, pumps running and things, so auto ignition temperature is important. Vapor density is important, another parameter that's worth looking at here as well, because of course some vapors and gases are heavier than air, will sink to low level, where others like hydrogen are very buoyant and will rise very rapidly. Minimum ignition, and when we're talking about minimum ignition energy for flammable liquids and flammable gases, generally, you know, they're orders of magnitude lower than we see for solids and powders. Therefore, we need to make sure that our earthing is very good and take precautions to prevent the charge build-up on liquids. So you'll see there things like trying to avoid splash filling, because creating aerosols and mists will generate a lot of charge. Impacts onto the side of tank walls and things can create charge, all of which you've got to get rid of effectively, otherwise you could potentially have a static discharge, okay? Or we could inert, which is getting increasingly common in flammable liquid storages. But having said that, there's still plenty of atmospheric storage vessels out there. And for extraction systems on flammable vapours or on liquid storage tanks, again becoming more and more common primarily because of environmental legislation. But again, flash point is important because that will determine how much vapours are given off. LEL concentrations, if we can operate below the LEL by providing sufficient ventilation, or in fact operating above the upper explosive limit, can also keep us safe. Knowledge of the R2 ignition temperature, the MIE again, and possibly limiting the oxygen concentration. So you can see hopefully that there's many ways of killing a cat, but we need to understand about our substances that we're dealing with. Only then can we design appropriate unit operations to keep ourselves safe in preventing these fires or explosions, or having the confidence that if we did have an ignited event, we're not going to be harmed because we can deal with the ignited event. We can either contain it, vent it to a safe location, or put it out very rapidly. So that's all I wanted to say for today. So I hope you found it interesting and enjoyable to sit and listen to me for an hour. If, as is normal, you have any questions, would like to discuss anything, would like any help going forward on your own plants with any of these sorts of assessments, or help in dealing with the processes, then just email us at info@sigma-hse.com, or get on the phone and talk to us, and we'd gladly come and help you. So on that, I'll say goodbye. Enjoy the rest of your day, and hopefully we'll meet again in a month or two when we do some more webinars on similar but different topics. So thank you very much for listening, and goodbye.